Hello everyone and welcome to another episode of the Hidden Quantum Champions. Join me along as we discover today another company from the magic world of the quantum economy. And before we start off, as always, make sure to grab yourself something to drink so we always stay hydrated. And let's get started right away with the company of today's video, which is Universal Quantum. So here we are as per usual on the website of the company. It says, solve, scale, develop new materials, accelerate drug discovery, optimize logistic flows, develop better batteries, accelerate neural networks, optimize encryption. So these are all, let's say, areas that we've seen already previously in other videos of this series that are promising for, let's say, quantum computational technology. And with that, let's scroll down a little bit and see what the website is actually telling us. So it says, solve, scale, change world. Quantum computers have the potential to overcome some of humanity's greatest challenges. To realize this potential, we need to build machines that scale. This is what Universal Quantum does. So we see they say they are in the space of building machines, and I guess with machines we are talking about something like quantum computers or quantum calculators, right? So otherwise we wouldn't see these optimization challenges up there. But let's see how they are actually doing it. So here it says who we are. We are a team of passionate engineers, scientists, and operational staff driven by a shared mission to build the technology that will transform our world. Then you can learn something about the story. What we do. We are building utility-scale quantum computers based on a robust, modular, and practical blueprint in partnership with the leading organizations and investors in the field. Discover our technology, and we will do that in a moment. And then it says, work with us. There's some advertisement here, followed by this, which says follow the journey. And I guess what we are seeing here is some type of news articles or articles that they are publishing. And then, well, we see here there are some social media links and so on. Okay, so let's go up again and go to who we are tab. So solve, scale, change the world. That's what we've seen already. Our mission, a quantum computer harnesses the fundamental forces that govern the physics world. It can efficiently model complex systems in ways that would take the best classical computer millions of years and so help revolutionize drug design, climate modeling, battery chemistry, and many other vital processes. To achieve all this, we need to make quantum computers work reliably at scale. We started Universal Quantum to meet this challenge because we believe that doing so, we can help to solve the most difficult problems faced by humanity. We are following a pragmatic engineering-based roadmap to build a device that is useful in the real world, a quantum computer that has utility. Every approach we take, every solution we devise is geared toward this goal. Solve, scale, change world. So here we see that scaling is discovered as the main challenge here, and that an engineering approach is being taken, which is based on the idea that, okay, we first have to solve the scaling problem, which is apparently the most pressing problem here, and then we can use this, or they can use it to change the world. So our story, Universal Quantum was founded by Sebastian White, professor of quantum computing and entrepreneurship at Winfried Hensinger, professor for quantum technologies, long-standing friends and collaborators at the University of Sussex. In 2017, Sebastian and Winfried published the first practical blueprint for large-scale trapped ion quantum computers. Sharing a deep belief in the technology's potential to change the world, they incorporated UQ the following year to harness the investment and engineering capabilities needed to make this potential a reality. Since then, they've reached major technical milestones, for example, connecting quantum modules at near perfect fidelity with our UQ Connect technology. We are also proud of our growing team and our Center of Innovation Excellence in the UK, along with sites in Germany and the USA. We are now producing our next generation of devices for clients, including the German Aerospace Center DLR, as we continue our progress towards useful large-scale quantum computing. And then here we see three promises from Sebastian White, CEO of Universal Quantum Computing, to our UQ family. You will always be my top priority. To our partners, I will move heaven and earth to help us build quantum computers that deliver true utility to you as quickly as possible. To the world at large, I will ensure to the best of my ability that our quantum computers will not only tackle humanity's biggest computational challenges, but also help to remove inequities around the world. Then a snapshot of the team here. We see engineers, but also a head of business development and others. Here we see the supporters, including Hoxton Ventures, but also what else do we have here? Main Sequence and others. And that's probably, let's say, the short image of the company. So as we already saw, they are working on ion trap technology, right? And I guess here we will learn a bit more about their approach. So what means scaling to meet the demand of 1 million high quality qubits, and when to keep going? This is how we're solving scale. Our technology is robust from the qubit up. So very nice animation here also. So there we have, I guess, the qubit. Our trapped ion qubits are well isolated and highly controllable through our unique chip architecture. So this is, I guess, the ion, and here we have the chip below it. So how does it work? We see that like the ions can move across the chip. Here it says that means we can deploy best-in-class error correction algorithms, making the system efficient, whatever our customers apply to it. And then we see that like here these ions can be shuffled and moved around. And that's, I guess, the, let's say, more chip-looking like design. It says we then integrate classic control units directly with the quantum chip layer, increase speed and reducing noise, and laying the foundations for truly modular architecture. So I guess this is the architecture, the different layers. Together, these elements make up the IQPU, the Integrated Quantum Processing Unit, a powerful basis for million qubit systems and beyond, built to integrate with our digital infrastructure and deployment plans. The link modules using UQ Connect, an electric field link that transfers qubits directly between our IQPUs at world record speed and fidelity. So that means basically, as far as I understand, the ion itself is the qubit. So you can use the ion to encode information. And then you basically can move the ions around to have them interact with each other to create a qubit, let's say to create multi-qubit gates, for example. So you need different systems, different qubits to interact with each other. Therefore, you need to physically shift them around. Now, the thing is, if it takes too long, errors will start to accumulate. So you actually have to be able to move them quickly around. And that's what they claim here is happening at world record speed and fidelity, so very precisely on their systems. This modularity and connection speed create a practical route to utility scale systems. Okay, and it goes on to say to operate the systems, we use UQ logic, an ultra-efficient microwave technology that can control qubits at any scale. And microwave technology in the context of ions is something that we've also seen already with other companies in the field. So there are also competitors that use a similar type of technology. And if you haven't heard about any of those yet, I would recommend you to check out the Hidden Champions playlist with all the other companies that we've seen so far in it. There are also some from the field of ion traps. Let's move on here. So here we see it, the single qubit gate. With only a handful of gate fields, we can execute single and 2 qubit gates on any chosen qubit at any scale with near perfect individual addressability. So the 2 qubit gates with only a handful of fields. Okay, that's the same story again. So yeah, we saw here the animation. So this is like single qubits. Now we have 2 qubits that interact with each other. And if you have single qubits and 2 qubit gates together, then okay, you can use that to build a quantum computer, a universal quantum computer. So we use existing manufacturing technologies to build the key components to our quantum computers. That's, let's say, the next key component here. Integrated classical controls remove the wiring problem that often limits system scale. Our system runs at 70 Kelvin, much easier to achieve than the millikelvin or 4 Kelvin temperatures required by most other approaches, especially at scale. Now, very quickly about the Kelvin scale. So the Kelvin scale is basically an absolute temperature scale. 0 is the lowest reachable or not even reachable temperature, right? And then from there on it goes up. Now it might seem that 4 and 70 is not so far from each other, but just quickly to say, what does it practically mean? If you had, for example, some solid state system, and that's oftentimes what the millikelvin stuff is also referring to, you're talking about, for example, a chip that you want to cool down. So 70 Kelvin is something that you can more or less reach with liquid nitrogen. Liquid nitrogen is kind of broadly available. You might know it from the school. There might have been some chemistry class or some physics class where someone was pouring that like bubbly, boily liquid nitrogen that creates this magic fog to, for example, cool down a superconductor. So this is, or there are even, let's say, ice cream places where you can get liquid nitrogen ice cream. Now for the 4 Kelvin, things become a bit more complicated because you cannot reach that with liquid nitrogen anymore. For that you need liquid helium. And the difficulty with liquid helium is, one, it takes much more energy to actually liquefy it. But then also it is much more rare of a material, because liquid nitrogen you can basically just produce from thin air, literally. Whereas for helium, you actually have to kind of purify it first. So helium is actually a noble gas, right? So it's a little bit, well, it's more rare, it's more difficult to find. And then also you cannot just evaporate it away, because when you evaporate it away, you basically end up with nothing again. So you would technically need to kind of collect it again in order to keep it in kind of a closed loop. So suddenly you not only have the cooling problem, but also the closed loop. And then when it comes to the millikelvin that they're talking about here, this is even more complicated, because this is also usually based on helium in these refrigeration systems, but actually on 2 isotopes of helium. So there's helium-4, which has 2 neutrons and 2 protons in its nucleus. And then there's helium-3, which has 1 neutron less. So it has 2 protons, again 2 electrons, which gets it the second spot in the periodic system. But there's only 1 neutron in there, which means it's even more rare, because it's not, let's say, the typical natural form that you find most in the universe, the most stable form. Well, it is stable, but it's more difficult to find, which means you again have to separate the classical helium-4 and the helium-3, and that makes it even harder. And you need basically both for this millikelvin range. And that means you suddenly not only have the cooling challenge that you need a lot of power, but you also have this very rare type of helium that you need, and that makes it even more challenging. So liquid nitrogen is kind of an easy one. nowadays with technology, but as soon as helium is getting involved, things become more complex. So that's one of the few reasons why you might want to go to liquid nitrogen temperature. Also, usually the cooling power, if you have, let's say, a fixed amount of energy, for example, is much higher at liquid nitrogen level than at liquid helium. So, and then it says our systems are designed to be integrated into existing computing infrastructure. So I assume we are talking about server rack size, like what is in a supercomputing center. So, and we are creating the full stack that supports utility. We work with partners from governments, industry, and academia to build the quantum computers of the future. And then what else do we have? And with them, we are developing and mapping the use cases for an error-corrected quantum computer utilizing our advanced system simulators and quantum algorithm expertise. Read about our work with the German Aerospace Center DLR here, and then there's a report link there. To us, solving scale does not just mean building scalable quantum hardware. Together with our growing ecosystem, we are solving scale for the full quantum stack. This includes, and then we have here the other challenges, scalable hardware, efficient error correction, software to manage and control at scale, and quantum algorithms for fault-tolerant quantum computers. It's important to point this out again here, what they say, which is together with our growing ecosystem. So they really want to play this as an ecosystem game, not just as they solving all of these different problems, but really more as they building the scalable quantum computing chip, more or less, and everything else that evolves around it is an ecosystem play, which is being played together with others. There's even more coming here. So classical compute infrastructure integration, and then utility generating use cases for clients and end users. So working here, there's a couple of points about what they're doing. So how we do things here. We've got a mission, it's exciting, but it's also a challenge. To meet this challenge, we need to bring our best selves. We do that through a culture of mutual care and respect that values our different perspectives, and with working policies that allow space for our individual lives. If you share your curiosity and determination, you will feel welcome and empowered here. So pioneer the future, always be error correcting and fault tolerant, embrace entanglement, and make your own superposition. And there's also something written here what these different statements mean. Then we have this section here, which is what it's like to work here. We are proud of our team's diverse backgrounds and life experiences. The more perspectives we share, the better we are at finding solutions. And as an organization, we benefit by representing the world we seek to change. But we also know that curating true representation is a perpetual mission. We want our employees to feel valued and empowered to fulfill their potential. That means, and then we have some common values here. We set our own approach to our tasks and responsibilities, trusting that we know how to do our work best. We build a sustained focus on well-being and mental health into our working policies and culture. We offer an unlimited holiday allowance that does not just mean breathing space, but a complication-free approach to medical appointments and any time we might need for personal or family issues. Our parental leave scheme is balanced and generous, focused on the needs of our family and adaptable when those needs change. Our regular social events are designed to create an oasis for team bonding and fun. Then we have this highlighted part here, which says, whatever the shape of our life, however you need to interact with the world and the people around you, your talent drives our mission to solve quantum computing at scale and change the world. And then we have here some voices from Universal Quantum. So some people that are working here and some open positions in the careers. Further on, we also have a knowledge hub here, which includes news and technical resources. We see those news articles linked earlier on the starting page, and there's a couple more down here. You can also divide them into podcasts, company news, so they also seem to have a podcast here. And a technical blog, which I guess is going into the more technical side of what they're doing, as well as a contact us button. And with that, we are already at the end of today's video of this very beautifully designed website. I hope you liked it. If so, please make sure to give the video a thumbs up. And if you don't want to miss out on the next one, make sure to subscribe to this video. As always, make sure to stay hydrated and see you in the next one. Bye bye.